In this video, we're going to introduce equations of lines and planes in 3 dimensions. So first we'll tackle lines, and lines are pretty analogous to finding lines and equations of lines in 3 dimensions is pretty analogous to finding equations of lines in 2 dimensions. We basically need to figure out a point the line goes through and the direction in which the line goes. So here's just one in 2 dimensions. So the thick black line here is just the line that we're interested in figuring out an equation for. We've got a point on the line, and we can think of that as the terminal point of a vector r sub 0 or r naught. And then we have a direction the line goes in, and we can think of that as v. So this line, the black line, is parallel to v, and then the r naught shifts it up away from the origin, so many units. If I look at doing any scalar multiple of v and translating it onto the line, any scalar multiple of v lands on the line if I've translated it by that vector r naught. So I can think of the line being traced out by the tip of the vector r naught plus t times v. That r naught does the shifting up to the line, and the t times v will stretch or compress or reverse direction for v, so that eventually we get the entire line drawn out. So, to summarize that, if we want the line that passes through the point x naught, y naught, z naught, and in the direction of the vector ABC, we're first going to let that vector r naught be the vector that starts at the origin and goes to x naught, y naught, z naught. Then, like I mentioned before, any point on the line can be described in terms of the sum of r naught and some multiple of v. So this is just going back through the picture that we did before. P is the initial point of the vector. The terminal point is on the line. The vector PQ must be parallel to v, so then P times Q has to be, or excuse me, the vector from P to Q has to be some scalar times the v. Now, how do we find PQ? So PQ can be found by doing x minus x naught, y minus y naught, z minus z naught. So we know that that particular vector from P to Q has to be a scalar multiple of the ABC. We can rearrange this a little bit. We can split up this vector into a difference of 2 vectors and then move the x naught, y naught, z vector over to the other side. So then we have that the vector x, y, z has to be x naught, y naught, z naught plus t times ABC. To write this in more of a vector form, we think of this as a function of t, where we plug in a t, we take the scalar multiple of v, and then add on the r naught. So all of this stuff is making precise what we mentioned on the previous slide. Let me scroll back there real quick, just so we can get the picture again. This would be our point P. This would be our point, or any point on the line Q. Then the vector from P to Q is this TV. And we find because it has to be parallel to V, right? It has to be on the line. It's pointing along the line, and V points in the direction of the line. So it has to be some scalar multiple of V, and we can find the P to Q by doing terminal point minus initial point. We refer to this as the vector form of the equation of the line. We can also write this in what's more of a parametric form if we just look at each of the components separately. So combining the components on the right-hand side, you would get x naught plus at for the x coordinate, or the component, the y naught plus tb for the y component, the z naught plus tc for the z component, and you can write those as parametric equations, and then we call those the parametric equations of the line. Finally, if we solve each of those 3 equations for t and we put them together, we get what's referred to as the symmetric equations of the line. So we've got 3 different forms here. We've got a vector form, we've got a parametric equation form, and we've got a symmetric equation form. So let's see if we can do an example that looks at all three of these forms. Let's say we want to find the vector form, parametric equations, and symmetric equations of the line that passes through the points 4, 2, 0 and 1, 5, negative 4. First, we're going to find that direction vector. We've got to go from one vector to another. So we'll do a terminal minus initial. So in this case, I've treated the second point like the terminal and the first point like it's the initial. Doesn't matter which one's which, because we're going to do all possible scalar multiples. It doesn't matter if you reverse the order, because you're going to do all possible positive multiples and all possible negative multiples. If I do the terminal minus initial here, we get negative 3, 3, negative 4. If I use the second point as my terminal point. Then the vector form is we choose one of the points. I chose 4, 2, 0 to start with, and then we do scalar multiple of the direction. Parametric form is just taking the x, y, z and writing them in terms of x, the first component, second component, third component. Symmetric form is taking each of those and solve for t and equating them. So we'll get negative of x minus 4 over 3 equals y minus 2 over 3 equals negative z over 4. So some special types of lines that we'll talk about, just like in 2 dimensions. Well, we can have this also in 2 dimensions, but in 3 dimensions we talk about lines being parallel as well. We say that 2 lines are parallel if their direction vectors are scalar multiples of each other, or that's exactly the definition of 2 vectors being parallel to one another. 2 lines are called skew if they don't intersect and they aren't parallel, so their direction vectors are not scalar multiples of each other. So here's an example that asks us to determine whether or not the 2 lines r of t equals 6, 1, negative 8 plus t times 1, negative 2, 3. And another line, which is q of s, equals 0, 4, 9 plus s times negative 2, 3, negative 5. Are these lines intersecting lines? Are they parallel lines? Or are they skew lines? Well, we notice that the direction vector of the first one is a 1, 2, negative 2, 3, while the second one is a negative 2, 4, negative, I'm sorry, this should be a negative 2, 3, negative 5. That's a typo there. In any event, if I take 1 times negative 2, I would get the first component. But if I do the negative 2 times the negative 2, I don't get the second component, which should be a 3. This should be a 3, not a 4, because we're taking it from that particular vector there. My apologies again. So, in particular, the second direction vector is not a scalar multiple of the first direction vector. So these lines are not parallel to one another. So, let's see if they intersect. Well, they intersect if we find a value for t and a value for s, so that when we plug those values into their respective vector forms, we get the same vector. The lines end up going through the same point. So we have a system of equations here to solve. We would have 6 plus t naught has to be negative 2 times s naught, equating x components, right? 6 plus t naught times 1, so that's a 6 plus t, has to equal 0 plus s naught times negative 2, or the negative 2s naught. Do the same things for the y components. 1 plus t naught times negative 2 has to be 4 plus 3 times s naught. And then finally, negative 8 plus 3 times t naught has to be the same thing as 9 plus negative 5 times s naught. So let's solve the first two. What we're going to do is we're going to solve the first 2 equations for t naught and s naught and see if those values also make the third one true. So let's see. Multiply the first equation by 2 and add to the second. We'll get rid of the t naught. 2 times 6 is 12, plus 1 gives us 13. 2 times 0 plus 4 gives us 4. 2 times negative 4 plus 3 gives us a negative s naught. So that tells us that s naught has to be negative 9. If I put in negative 9 in for s naught, you can solve for t, and t has to be, the t naught has to be 12. Do those values give us a true statement in the third equation? Well, it turns out the left-hand side will be 28, while the right-hand side will be 54. Since that's a false statement, that tells us that we do not have a common point for the two lines, or in other words, the lines do not intersect. We already showed that they were not parallel, and since they do not intersect, they are skew lines. So let's switch over from lines to planes. We need to figure out a point on the plane, and we need to figure out a direction on the plane, much like what we do for lines to find their equation. But the direction that we're going to be interested in this case is not the direction that's parallel to something like we did for lines. Turns out that we want the perpendicular direction. So let's see why, and I'll go back to that screen in a second to show the picture. But for planes, we need the normal direction, or the perpendicular direction to the plane, and let's see why. So let's go back to the picture here. Here's a couple of vectors in my plane here, or what have you. Here's a point in my plane. It doesn't really matter if I go this direction or this direction or this direction. It doesn't matter how I'm in the plane. If I know a vector that's perpendicular to the plane, it has to be perpendicular to every vector that's in that plane. So if I have a starting point, if I want to go to from x naught, y naught, z naught to some other point x, y, z, then the vector between those 2 points would be perpendicular to the n, no matter where I move that other point, if I have a fixed point in the plane already. All right, so let's let n be the vector ABC. I suppose it's perpendicular to every vector in the plane, and start with the point x naught, y naught, z naught in the plane. So if I have another point in the plane x, y, z, and I do the vector that has initial point, the given point, and terminal point, the x, y, z, then that vector must be perpendicular to n if the 2 points are in the plane. Well, we have an easy way to determine if two vectors are perpendicular to one another. We can take their dot product. So we would need the normal vector n dotted with the vector from x naught, y naught, z naught to x, y, z. That dot product would have to be 0. Take the dot product, and we get a times the quantity x minus x naught plus b times the quantity y minus y naught plus c times the quantity z minus z naught is equal to 0. And that gives us a perfectly good equation of the plane, which we refer to as the scalar equation of the plane. Let's see if we can use that in practice. So let's say we want to find the equation of the plane through the points 0, 4, 0, 1, 3, 0, and 2, 0, 1. All right, so what we're going to do is we're going to find two vectors that have to lie in the plane. So let's pick one point kind of as our starting point, and then the other 2 points we're going to use to find vectors. So we'll use P as our starting point, our base point, if you will. And we'll find vectors from P to Q and from P to R. So we're finding from the vector from P to Q, again doing the terminal minus initial, you'll get 1, negative 1, 0. Finding the vector from P to R, we'll get 2, negative 4, 1. These are now two vectors that have to be in the plane that we're interested in. We are looking for a normal direction. To find a normal direction, we'll take their cross product, because we know that cross products give us a vector that's perpendicular to the two vectors that we're taking the product of. So going through our process for finding cross product, going through all that work, we should see that the vector minus I minus j minus 2k is perpendicular to both of the vectors that we have up here. Any scalar multiple of this vector will work. Well, since they all have minuses, and I don't really want all these to have minuses, I'd rather have them pluses just for aesthetic reasons, I can multiply by negative 1 and change them to all pluses. So 1, 1, 2 will work as a normal vector. You should be able to see that, right? If I take 1, 1, 2 and dot it with 1, negative 1, 0, I get 0. If I dot it with 2, negative 4, 1, I get 0. So we have a direction vector. We can use any of the 3 points as our given point, if you will. So in this case, we'll have 1 times x minus 0 plus 1 times y minus 4 plus 2 times z minus 0 is equal to 0. And if we simplify that, we'll get x plus y plus 2z equals 4. And here, for good measure, is an equation of the picture of the plane. It's not the greatest picture in the world, but it's a picture. P, Q, and R here are in the plane. Here's my vector from P to Q. Here's my vector from P to R. We found the cross products, and that's what the n vector would be denoting here, is the idea of this cross product.